Hi everybody, my name is Raul Navarro. I am a professor of chemistry here at Occidental College, and I know many of you are familiar with me as a professor in the classroom, but today I'd like to share with you some of the research that I do here. So let's dive in. At its very core, organic chemistry really is all about carbon, the one element that permeates our everyday lives and makes our lives possible. Part of what I find so fascinating about carbon is that you can get remarkable complexity from a single atom. For example, carbon atoms comprise the core of very simple molecules like glycine, pictured here, which you can see is made up of carbon that is bound to nitrogen, oxygen, and hydrogen atoms. Next to it, you see the same molecule represented in a simpler way with these lines representing these carbon-carbon bonds. It carries the same information you see on the left, but makes it easier for us to draw more complicated molecules, as you'll see in a minute. But back to the point. When we take simple molecules like glycine, an amino acid, and start to stitch them together, you give rise to peptides, as you can see here. And once you start to forge more and more bonds and add more bonds to this peptide, you start to give rise to the formation of proteins, as you can see caricatured here, which are the workhorses of our bodies. Think hemoglobin carrying oxygen to your body. The same can be said for molecules like adenine, which you see down here, a DNA base pair drawn in full and simplified forms. These can interact with one another, as you can see pictured here in the middle, through hydrogen bonding, and before you know it, you accumulate so many of these interactions that you generate the sort of beautiful architecture that is DNA, which carries our genetic information. The bonds that carbon can forge with itself and other elements also makes possible what are known as natural products, or naturally occurring, often complex-looking organic molecules that usually have some interesting biological properties. You can see examples of them on this slide. One example is penicillin, an antibiotic that many of us are familiar with and is ultimately available to us thanks to the fungus that produces it. Other medicinal compounds like Taxol and Artemisinin are ultimately obtained from plants, as you can see here. One of the goals of research labs like mine is to find efficient ways to make these molecules in the lab. Now, I know what you're thinking. If nature makes these molecules, why do we need you to make them? Your point would be well taken, especially if we consider the success that is penicillin. In fact, soon after it was initially discovered, scientists were able to devise elegant ways to coerce this organism to produce it on an industrial scale, which came in handy to treat bacterial infections, especially during World War II. With penicillin, I would say this is a solved problem. We don't need a chemist to make more of it. But the same cannot be said for most other natural products. Take artemisinin, for example. Artemisinin is an anti-malarial natural product that is isolated from this plant, Artemisia annua. The plant itself produces artemisinin at a very small percentage of its dry weight. If we're being very generous, we might estimate that a kilogram of dried plant would produce 1 gram of artemisinin. That may sound like a decent amount of this compound, but when you consider the fact that this is barely enough to start dosing even one person, you can start to imagine how incredibly inefficient it would be to grow a ton of this plant just to harvest it and obtain enough of this molecule to treat an entire population of people. So this is where organic chemists like myself come into the picture. We ask ourselves, can we make these molecules in the laboratory? And better yet, can we be as or more efficient than nature is? Now that I've laid out the motivation for our research, now we can think about how we as chemists go about developing and executing a strategy to make organic compounds with medicinal potential. One way to conceptualize what we do in the lab is to think of it as putting a jigsaw puzzle together, but with a few missing pieces. To elaborate on this analogy, suppose you are trying to make or build compound ABC, a biologically active natural product. You have several pieces at your disposal. Some of the pieces are fragments of your molecule, highlighted here in blue, while other pieces, in purple and red, represent the chemical reactions that allow you to marry or bond two molecule fragments together. Having this purple piece at your disposal, for example, which you plan to use to make a bond between compounds A and compound B, is analogous to searching the chemical literature and finding reaction parameters or conditions that have been previously developed by other research groups and applying them to your two fragments. Part of the purpose of research comes into play when you're missing the chemical reaction or puzzle piece that you think you will need to make the final molecule. For example, you might think in the lab, it would be really efficient if I could put compound AB and compound C together to make my target. But the reaction I want to implement isn't known or well developed in the literature. As organic chemists, part of our goal as we endeavor to make these complex molecules is to also develop new, more efficient tools to build them. The excitement comes from not just making the molecule itself, but from the discovery of these new reactions. With this background in mind, research in my lab can be divided into two camps: natural product synthesis and what we call methods development. To summarize our efforts in regards to natural product synthesis, my lab is currently trying to develop an efficient way to make swear-lactone A, a natural product that can potentially be used to treat hepatitis B infection. In practice, my research students and I use well-precedented reactions to start making the molecule from fairly simple building blocks, and we also hope to develop some new chemistry to efficiently make the core of the natural product. I've had several undergrads who have really pushed this work forward, so I have them to thank for the progress that we've made so far. I'd like to focus more on the second branch of our research program, which lies in methods development. In contrast to total synthesis, where you devise a sequence of steps to access a complex molecule, a methods project really hones in on one specific transformation and asks the question, can we get this unprecedented or new reaction to work, period? It's akin to discovering some of those missing puzzle pieces that we discussed earlier, but in this case, you're really stripping down the molecule to something that is very easy to make and evaluate. In our case, we wondered if we can forge this specific carbon-carbon bond here by using a palladium catalyst from this fairly simple substrate or compound. I'm excited to report that we've been able to identify a catalyst and reaction conditions that facilitate this reaction in excellent yield. This work was really pioneered by Cheyenne Orozco, one of my first research students, and is being followed up with more thorough studies as we speak. I currently have 3 research students this summer, Connor, Tim, and Gisela, who hopefully by the end of the summer will have acquired sufficient data to put together our first peer-reviewed publication, so be on the lookout for that. And that's our research in a nutshell. If you'd like to learn more or want to get a better sense for what our research is like on a day-to-day basis, you're welcome to check out our group website, navarro.oxycreates.org, or you can check out our Instagram page, the Navarro Group. Thanks for tuning in, and until next time,